We have uh, Rohit Johnson from PNNL. He is a colleague of mine, but definitely out of being a colleague, Rohit is also the team lead for the cyber physical test beds at PNNL. He leads a lot of efforts in the digital twin and the cyber physical domain. Rohit has got his bachelor degree in electrical engineering from Sardar Beral College of Engineering in Mumbai, India. His master's and PhD from electrical and computer engineering from Georgia Institute of Technology. He is also currently the research engineer with the PNNL, and his current research interests include decentralized control methods for smart grids, working on high fidelity real time simulations, equity aware planning structures, and resilience evaluation schemes. Um, I leave the floor to you, Rohit, to if I missed anything, to go ahead, and then you'll have the time to present today our talk about the role of cyber physical test beds in future proofing grids. Thank you.
Actually, sounds good. Thanks so much, Michael. Let me go ahead and quickly just make sure that my screen share is working correctly for everyone. Let me know when it comes up on your end.
It is.
Okay, that's great. So yeah, I'll just go ahead and get started. So yeah, like Michael mentioned, I'm a power systems research engineer out here at PNNL. Primarily, my work focuses on cyber physical test beds and their applications, either towards grid resilience or just understanding kind of threats in general. Um, so a lot of the work that I will be covering in this presentation is, a result of, effort that a lot of folks have put in. Captures kind of things that former colleagues as well as, current colleagues have kind of contributed to. Um, so with that, let's get started. Um, so, right, here we go. Um, so I am sure that most of the people on this call don't need kind of an introduction to, the need for having rigorous system evaluation at this point, right? We're seeing much faster dynamics on the system that were previously unprecedented. This has been going on for 2 decades now, mainly because of faster controls that are associated with faster DERs at the grid edge as well as sometimes at the bulk level. And then a lot of traditional analysis in terms of understanding how these things operate, as well as how to mitigate some of the issues that are caused by these fast controls, is focused on purely simulation-based approaches. But the reality is that, in today's grid, you have a vast number of localized control in terms of automation devices, in terms of protection devices, in terms of controllers that are reacting to local changes, as well as all of the toolboxes in terms of EMS, DMS, other management systems that kind of sit at multiple layers within the system. So to truly understand the challenges that come with faster acting controls and different levels of threats that exist on the system, we need to be able to model the system in the environment that it truly exists today. This means capturing the effect of all of those devices, their different response times, their different schemes, and then designing controls to mitigate some of the challenges that we're seeing in today's grid while accounting for all of those things. So to study future behavior of future grids, we need to be able to create an environment where prototyping for new controls can be done with all of these existing artifacts that sit alongside the grid currently. um, the approach that most people take is building a cyber physical twin for the system, right? They're extremely high fidelity environments typically where you can create realistic emulation for different aspects of the grid. So from a conceptual level, this would mean looking at the physical characteristics of the grid itself and finding a way to simulate that in as much detail as you can, right? Couple that with communication layers where you have all of the devices that we talked about interacting with each other, as well as your control set points coming in from different points on the network topology. And then you have the information and control layer where most of the sophisticated algorithms, which are centralized, kind of sit. And there's many ways to kind of go about designing anything that can be called a cyber physical testbed, right? This could be something like a pure simulation based approach where we, take, PSCAD models that in the thousands of nodes range, where you can, tweak the model with relative ease. So you have a lot of scalability and reconfigurability, and the cost is low, but the realism is, of course, kind of compromised, right? All of those devices, all of those interactions that we talked about kind of go away. On the flip side, you also have the ability to put in a large cost and build out pilot microgrids. We've seen a few of those across the country already, where it's as realistic as it gets, right? But the scalability and reconfigurability is low. So, you're kind of stuck with the configuration that you build. Your experiments can be rather limited. I'm guessing most of us on this call kind of operate within those blue and green boxes that you see out here, which are the hardware in the loop approaches, as well as kind of some test range facilities that you can build up, where we emulate certain aspects of the grid using high fidelity simulators. And then couple all of the other equipment, control, network interactions, on different layers, along with that real-time simulation to kind of something that can scale, something that you can reconfigure with a relatively, medium level cost, but high levels of realism. Um, so the facilities that PNNL operates out here, we call it PowerNet. Basically, it is a range of hardware in the loop simulators. We only have OpenRT real-time simulators out here with about 32 cores. Actually, that number needs to be updated on the slide. The ability to do kind of FPGA-based emulation for fast switching systems. Couple that with the traditional automation capability that you see out there in the form of RTACs, as well as protection devices like traditional SEL 351s, 451s, 751s. Um, all of these devices can kind of be networked in a specific way for whatever experiment that we want to run. Along with OpenRT's simulation platforms, we can also run other simulation platforms that are relatively low fidelity, anything from GridLab to OpenDSS as well, depending on the experiment's needs. But typically, I would say real time kind of tends to be our preference when doing these kind of experiments. We also have a bunch of other, controllers, relays, PMUs from a bunch of different vendors. The idea is that all the, specifics and nuances of how these different vendor equipments operate can kind of be captured, in a setting where, let's say we have a traditional grid model, we can put different vendor devices at different points on the system and see kind of the effect of that. We also have the ability to connect to one of the buildings on campus and bring it in as a load into our system. So there is some scope for power hardware in the loop. We do have an amplifier that the Opal can connect to, as well as a bunch of PLCs to simulate traditional automation. Um, so this is on the physical side, but on the network side, we also have a cloud stack where we can create a bunch of virtual machines and instances to create network topologies. So this would be spinning up machines to emulate any kind of a traditional communication scheme where data flows occur in certain ways. For instance, if you have a grid and you have grid edge devices, you may have flows that are kind of going up to an aggregator. The aggregator then sits somewhere on this topology where they can collect information, reduce some of the observability, and then talk to the system operator. The system operator may have something like a DMS sitting there, a commercial DMS, which we are also able to kind of model in, where control. I'm sorry, control actions can be taken on in real time as particular events occur. We also have equipment that can support natural gas analysis. This is slightly outside of kind of the domain that we're talking about, but we do maintain kind of an inventory of gas meters as well that you can use for multi-domain kind of analysis as well. So what does this do, right? This lets us take something like a real world or synthetic system, model it with a high level of realism, with the adequate amount of fidelity, and then really run, using hardware in the loop and controller in the loop approaches, and then really run kind of studies where we can understand the impact of normal as well as off normal events, as well as look at the vulnerability of the system in certain modes, right? All of this while emulating those data flows that we talked about on the network layer as accurately as possible. So the three main functions right out here, if I was to characterize kind of the nature of the experiments that we run, is understanding the threat to the system. And by threat, I mean not just from the cyber side, but also from the physical side, just events that can occur, whether it be weather resilience versus, specific attacks that are carried out on the system. How do we mitigate some of these with intelligent controls? That's the second part of that analysis. And then trying to figure out what kind of exogenous threats sit outside of this, right? Outside of the things that we expect. And I'll briefly touch upon each of those today. The initiative that this work is kind of a part of is kind of structured with different teams that sit across, different parts of this particular schematic. So I'll be talking more about the cyber physical twin here, but then there are folks out here who kind of exclusively look at the adverse conditions and their impact, looking at whether the level of fidelity that this cyber physical twin is modeled at actually captures what is needed for experimentation, as well as a range of applications where people prototype controls based on the data sets that we can generate from this cyber physical twin, conduct scenarios and evaluate resiliency metrics, as well as look at kind of attack graphs that can exist on a particular kind of topology. Um, so really, kind of the work, and again, this is kind of contribution from a lot of folks that were part of the initiative early on and kind of did a lot of this work, right? I'm just paraphrasing for them here, but the idea is that what is a cyber physical test bed and what are our use cases, and how does that define kind of the structure that the cyber physical test bed needs to mimic, the architecture itself, and then what kind of studies can we do on top of it, right? So like we talked about, realism and scalability were important factors in terms of the requirements itself that the folks that would like to conduct experiments on this indicated. Automation was another big one where, let's say we have hundreds of scenarios to run on a particular test bed. Can we make it relatively automated so that a user can not bother, about, what the cyber physical test bed actually looks like, how it operates, how it works, what platforms it interacts with. Moreover, just give us kind of a template, and we can run with that and automate a scenario for them. Right, makes it easier for someone who's prototyping controls to not have to sit and understand how the system operates. Couple that with orchestration, right, where we can queue up scenarios like a traditional server would, and go through those, generate data sets, and then kind of put those out for users to look at. And then the devices itself that we talked about, right? What are the relevant kind of devices from a control and physics perspective that we need to maintain? So all of those, I'm sorry, was there a question? Never mind. So all of those kind of led to this setup that has been built by a bunch of researchers out here at PNNL over the years, where there are five main components here. Component one here is of course those OpenRT simulators running real-time platforms where either on the CPU or the FPGA, depending on the level of detail that we're looking at or the time step that we're looking at, as well as whether we're looking at high frequency converter dominated systems versus just traditional power systems. Couple that with some of the control devices that we talked about. This could be anything from an RTAC where you have relatively simpler forms of automation to something else in the form of microgrid controllers or other things. Protection devices as well, which are number three out here, that are connected through hardware in the loop interfaces to our particular simulator. There's also the amplifier, which I talked about earlier, where we can the big gray switch out there, which allows you to bring in real world kind of devices like EV emulators or building control system in to our simulation environment, as well as the communication network that lets us model different topologies and data flows on the back end. So first I'll talk about kind of a medium scale model that we developed initially as part of this work. where this is a standard IEEE 123 model where we have modified it to have three microgrids out here. The model has been optimized to run on 7 cores in real time at a 50 microsecond time step. So we had to come up with different decoupling techniques to allow this to happen um, on the physical side itself. The little blue boxes that you see on the figure are, the SEL 351 relays. They control those particular breakers at those interfaces, and they're interfaced through, analogs and digitals with the simulator itself. So, as realistic as we can make it, right? All of these, points on the system have also kind of been set up to establish telemetry over DNP3 and Modbus. We also have a network layer that you can kind of see underneath where, different interactions between different devices can be captured. Um, and then we also have some small schemes like under frequency load shedding, some simplified controls kind of sitting locally within the simulation itself, along with, what you can do within the simulator, right? You can also have more relays and more relay functions that are purely emulated, not, interface through hardware in the loop approaches. So what this lets us do is now create a bunch of different scenarios on this particular test system, whether it be anything from component level where we want to prototype new grid forming controls at these particular inverters versus microgrid islanding scenarios which are somewhat in the middle, as well as kind of system collapse scenarios which are at the macroscopic level where we simulate failure modes, right? All of this with the controls protection communication kind of sitting in that same environment to allow all of those phenomena to be captured together at synchronous time steps. Like I talked about earlier, right, the orchestration and process flow was a big part of this because building a test bed is great, right? But the usability often depends on whether we can make it relatively easy for users to give us certain parameters that they want to change and execute and generate rich data sets that they can take in readable formats. And whether it is taking that and training, machine learning model versus just analyzing system modes, right? That becomes easy. So um, one of the initial things that we did was leverage kind of an API that sits around one of the platforms in the Opal environment. So we typically use HyperSim here, and the API kind of allows us to interface with the simulator and execute certain things at certain time steps. So we can take a list of user changes, whether it is anything from a step load change to, a step, change in terms of the topology itself in the system versus more complicated scenarios where we have multiple moving parts at different instances of time. We can orchestrate that through the API. Along with that, the orchestration mechanism also starts collecting network traffic from the instance the scenario started. So if we have interactions that are happening on the network layer at the same time, all of them are captured and later can be synchronized together. There's also the ability to orchestrate attack scenarios using MITRE Caldera that we've kind of built in for a few key scenarios. It's not, universal yet. Um, After that, we kind of take that data, process it out into readable formats like CSV or whatever else that users might need. Do some preliminary data checks just to ensure that data integrity was still there are points where scenarios are simulated and we see missing data. So this is just more of a quality check. We also generate some diagnostic plots for the user to visually see like almost immediately, so they don't have to dive into the scenario to see if what was asked for is not always what you get, right? So just it's another means of checking. So with this, we can create a 600-second capture basically of different scenarios within that window, both from the network and physical side, and get that back to a network location for the user. And we can do this recursively as many times as we want. Um, the attack orchestration is also another piece. It's primarily based on MITRE skill chain framework, where you can exploit the system in different ways. So with that, we've kind of created some orchestration for man-in-the-middle and command injection attacks on this particular topology that we can orchestrate at different instances in time. There's also the ability now where we have created hooks for a NS3 virtual network to also sit instead of this emulated network that we have here, where we can put in more complex topologies insert packets from the Opal simulator, put them through the virtual NS3 network, and then push them out on the other side to whatever central control entity that we modeled, right? So whether it is just an aggregator or a system operator or a DMS system, it will see it as real telemetry coming from the field, except, we can make the network as complex as we want. So with that, every scenario would basically be looking something like this, right? Where all the node voltages, real reactive powers, frequencies, set points, everything is captured over that 600-second window at a 500 microsecond resolution, which is mostly adequate for, any kind of studies that you see out there. Also, you'd kind of see all the packets that flow over the network during that particular point. So let's say we are simulating a cyber attack on the system, right? You can see those packets kind of exchanged, as well as, that particular packet where the command injection was done in your network capture. So with this, we were able to create a range of scenarios, roughly about 30 scenarios over the course of this project that have been used for different purposes. Anything from, system operating condition analysis to, cyber attack analysis. Recently, there is a transactions on smart grids paper that we also put out where we were able to train reinforcement learning models to improve transient performance for IBRs. And this system was actually the test bed that was used for it, where we collected data in extensive different modes of the system, trained a model, and then showed that we could mitigate certain conditions. So to give you an example here, right? I'll just show a scenario where, I talked about that blue box being an SCL 351 relay, right? So in this particular case, if we were to island the system, so attack that particular relay to open the breaker, and then microgrid 2 and 3 on this diagram would basically be islanded after that. That would be a forced islanding scenario, right? Sort of unplanned, where you aren't able to adjust kind of system outputs to make that a smooth transition. Um, so we actually did create an attack scenario where we could inject a packet, force the relay to open. So on in this data set, you would see that in kind of those packet captures that I talked about, where you see that packet coming in and the relay opening. And then on the physical side, you can see how things kind of get a little bit unstable. Eventually, of course, they stabilize, but there's these huge transients that you see because it's a forced islanding scenario. Um, there's also another scenario where we were able to create perturbations on set point signals that were being sent from a central control entity to one of the inverters on the system, where we were able to manipulate the power reference and the reactive power reference that they were seeing up and down, continuously, to create these sustained oscillations on the system. So um, you can kind of see here that one of these attacks would basically cause these sustained oscillations on the system. It's a pseudo-optimal mode, right? And these are, of course, very large oscillations which would traditionally be captured by a protection scheme. But if these oscillations were to be in a much smaller band, you could have a scenario where it kind of slips under the radar of your protection scheme, but you still see these kind of oscillations percolate through the system. So just another representative scenario to show kind of the effect, right? Um, Another thing that we noticed was particularly associated with inverter reconnection. So when you have grid forming inverters that are, tripped out of the system and they reconnect, the challenge is often that, the droop kicks in almost immediately and creates on reconnection and creates these huge transients in the, the power, because you're still synchronizing, right, at that point. So this challenge was actually something that the Unify Consortium, for those of you who are part of it, some of the folks on our side in the lab who work on that, kind of came up with a solution for, where it's relatively simple, right? The idea is that we, close and connect to the system with the droop disabled. Um, Basically show that we can match the voltage but not fully synchronize or reach our power set point. And then in step two, once we know that we're not creating these huge transients, start kind of moving towards your set point by activating droop. It's a very simple mechanism, but shows much better transient stability, right? And doesn't create those huge transients on the system. So we were able to prototype that on the system as well, and show some interesting results. So I talked about the 123 node system, right? It's a relatively medium-sized, traditional system that's been used for many different kinds of analysis. But there's some things that you just can't capture with a system of that scale, right? And these are real-world problems where you have mixed DER standards out there. You have emerging models like DER aggregators, energy storage aggregators, multiple third-party energy entities that can exercise control on the system, and they typically sit between the centralized control from the utility side, and the grid edge itself. So there may also be some loss of observability that the utility operator may see, because levels of control are different at different stages, right? So there's this different complex levels of interaction between different, not just devices, but also control entities on the system, that need to be analyzed, right? So to do that, one, we need a large cyber physical model, something that is far bigger than the 123 node system. We need to be able to model all of those agents in a relatively, easy manner and a scalable way where we can mimic these kind of topologies on the network side as well, and network and control side, I guess, as well, and then evaluate all of these scenarios, right? So that brings up the question of scalability, right? On the real-time side, a 123 node system, we could do it with 7 to 8 real-time cores. We could model about 6 DERs in there, a few synchronous generators or diesel generators, and some points of unbalance, right? But we wanted to kind of see if, we scale this to the, 30x level, right? Where you now have 3,000 to 9,000 nodes. So huge systems with a large number of DERs with different topology changes, different kinds of control that you can execute on them. The challenge with that one is managing the computational burden, right? So if a 123 node system took 8 real-time cores, the estimate is that something like a 9,000 node system would require about 32 cores, right? That's a huge computational burden to deal with. And the other thing is, the 123 node system, when we modeled it manually, it took us months to build. Something like a 9,000 node system would take, probably years to build out, right? From scratch if we were to do this manually. The other thing is it's also prone to human error at that point, right? How do you benchmark your models if, you make mistakes along the way and the system's so large? Um, so the first approach that we took was sort of a multi-fidelity approach. Let's break that large system, preserve some of the system in real time, and then keep some of the system kind of in a low fidelity domain. And to do this, we kind of leveraged a quasi-static time series approach in GridLab D, which is a low fidelity simulator, and then kept that high fidelity portion in HyperSim, and created interfaces using Helix, which is a co-simulation engine. It basically acts as a broker between two power flow engines, and you can look up the functionality for that. It's quite extensive. Um, so, but the challenge still remains, right? On the high fidelity side, how do we, efficiently take a part of that larger model and convert it, right, into something like HyperSim or, any other high fidelity platform? Um, so while this approach looks feasible and looks the diagram's pretty fancy, it doesn't actually help us solve that problem of actually creating the model in real time, right? So to do that, we worked on an approach where we were able to take low fidelity models. For instance, I'm showing an IEEE 13 node model here, and automate the process of converting it into high fidelity. So we worked with OpenRT and created some scripts of our own around their structure, their conversion tool, to be able to do this from GridLab D. We're also extending this to SIM at this point to make it more generic. But here you can see that an end-to-end conversion can be done relatively easily for most of the standard components that you would see in, the GridLab D framework. So this is just a 13 node model. But 13 node model you could have built by hand in 10 minutes, right? So wanted to show kind of this where we scaled that method to about 3,000 nodes, where we were able to take a part of that 9,000 node system that I showed, and create an end-to-end conversion where everything from the geospatial location of the nodes itself is captured, and you can see that the system looks exactly identical, but we are also able to benchmark the steady state flows across the system and validate that the conversion is accurate. So pretty confident about this tool working and makes it a lot easier for us to do these studies, right? So the idea is, depending on the experiment that you are engaged in, the system size requirements, the complexity requirements, a user may be able to create a low fidelity model, not necessarily worry about how things work in the high fidelity domain, and then we can make that end-to-end conversion for them work and create kind of a test bed setup that works for them, and then leverage that same orchestration that we talked about earlier. The second approach to scaling that we were considering is something we explored last year called scalable hardware in the loop federated test beds. The idea here is let us scale up as much as we can using the capability that we have on our side, but then let's federate with another entity out there to create, a larger, more complex system. For instance, a natural fit is something like TND, right? Where some other entity may have a extensive transmission test bed out there in high fidelity, um, that can be interfaced to our distribution test bed, and we can make all of those sandboxes work together in different ways using telemetry between these two entities. So while this approach was initially floated, we're still kind of looking for partners. Happy to talk offline if there is interest as well. um, so scalability apart, right? If we go down to the component level itself, we're seeing more and more converters out there that switch at 100 kilohertz or more, right? Especially, something like solid state transformers or medium voltage technologies that you see out there currently. Even MMCs, right? They're quite challenging to analyze with, the time step size that we have. So one of our mandates, and this is under kind of the GMLC program, there's a project called Merit where we're investigating medium voltage solid state transformers and their applications on the grid. Is how do we model these fast switching converters and then conduct meaningful analysis on medium voltage topologies, right? Um, so again, this is something that we've been working with OpenRT on, where we're trying to leverage CPU plus FPGA based approaches. The idea is that you keep most of your slower controls as well as the system definition itself. So whether it's an IEEE 39, 34 bus system that you're modeling right on one side, on the CPU, which has been done before, but then take the fast switching power electronics and emulate them on the FPGA that allows you to kind of reach that nanosecond level time step. Um, so this is something that we are currently exploring. We're also exploring grid forming controls on our end right now at the lab, where we're exploring CHIL approaches, where we can take generic forms of control, program them relatively easily on DSP boards, interface them with the Opal system, and evaluate them in different ways. So we talked about threat awareness, we talked about mitigation for kind of some of the things that we see on the system and ways to model, systems in ways where we can analyze this. But what about exogenous factors, right? What about the human in the loop, right? There's often an operator that sits behind an EMS or a DMS system at a centralized control entity, and is coordinating certain things manually, right? Even though there are more applications now that are more automated and automation sequences are prevalent, there is a certain level of reluctance from the operator side to rely on automation sequences extensively, right? So can we model that element as well in addition to this cyber physical twin? So we've been trying to do that over the last 2 years, where we're creating a TND co-simulation environment where we have transmission emulation in Power World Dynamic Studio, where we can set up telemetry for certain points, whether it be anything like AGC to just understanding what the system voltage and frequencies are over a realistic communication network. On the distribution side, we kind of leverage the systems that we talked about earlier, right? The 3000 node or the 123 node system on the real-time simulator and HyperSim, and similarly kind of set up telemetry on that side. We've created a co-simulation bridge where there is a exchange every few time steps between the TND simulator to converge in some ways as a TND co-sim, right? Setup. But on the other side, we've also set up kind of a EMS tool, which can allow its sandboxes, whatever they are, right? Whether it is setting AGC control set points, making topology changes, all the automated sequences that we can interact with. We've been using GE Terra as kind of the system of choice there. On the distribution side, we have an in-house DMS tool that DMS-like tool that lets us basically emulate the functionalities of DMS, but it's open source, so we can create new applications like transactive estimation, state estimation, that we can relatively easily script in Python and plug into this setup. We call it Grid Apps D. It's quite a mature tool. It's been around for a while now. Recently, the functionality to take in field measurements was added, so it made sense to use it as a DMS out here. The idea is to now use this entire setup to put operators in the room, emulate training exercises, create contingency scenarios, and understand their response time, as well as kind of the shortcomings of these management systems as well. Um, so hopefully I kind of covered a good amount of efforts that PNNL is engaged in out here, along with its partners. Hopefully the point that high fidelity cyber physical test beds are essential was conveyed, that we need to create this environment where we can allow all of the controls, protection, communication to exist together to understand how the system behaves in normal and off normal conditions. The problem of scaling this setup is often challenging, but hopefully I kind of showed you a couple of tools that we can use, that we have been working on here at PNNL, to allow that scaling to happen. And then it's extremely important to create kind of orchestration and support tools that can allow users who may not understand how cyber physical test beds work to interact with this particular system through automation or whatever have you, right? To allow rich data sets to be produced that can actually benefit someone. Most of this work was funded through an internal LDRD program here and under the RD2C initiative, but also part of the GMLC merit project that I talked about, the MV converter investigation that we're carrying out. And with that, I think I can end my presentation. Happy to answer questions.
Thank you so much, Rohit. This is great presentation and great work. And now leave the floor for questions. If anyone have a question, please feel free to put it in the chat, or you can come unmute and address your question. Um, I have a question until someone comes with a question. Uh, this is a lot related to different aspects from a cyber physical perspective, either hardware in the loop, human in the loop perspectives. How would this be used or leverage it to go forward and have a more comprehensive, I would say, digital twin perspective from an operational perspective?
Yeah, I mean, I think from an operational perspective, right, hopefully the idea is to at least have the same control mechanisms that are typically used in the loop. So whether it is typically you would think about, a SCADA system, right? And kind of the automation around that SCADA system. If we can emulate that to a good level, you can create the same operational environment that a particular operator sees, right? Um, but with the advantage that on the side where we are emulating grid dynamics and the physics of the system itself, you can now start creating interesting scenarios, right? Where synthetic scenarios, of course, but to the operator sitting behind that EMS toolbox, it looks very realistic, as if it's actual data coming in from the field. So it's a controlled environment where you can now um, almost understand how those applications that sit in the EMS setup may fail under certain contingency scenarios, and have kind of a perspective of how to go about changing that automation scheme. So that's kind of the realism aspect that I would say. The cyber physical twin itself is only able to emulate kind of a synthetic grid, right? But the idea is if we can make that synthetic twin as real as possible or as close as possible to what you see out there, the scenarios become more realistic. And operators can go through different modes of the system in a more realistic manner.
Gotcha. Thank you. Any question from the audience?
After
Well, I don't see any questions. So maybe we can wrap this up earlier today if no questions. And again, I would love to thank you, Rohit, for your presentation. This is great. And for all the members of the task force, we're going to send the announcement for the next bi-monthly meeting, which probably will happen in January with the information about the next speaker. And keep an eye on the emails. Thank you all for attending, and thank you, Rohit, again. Enjoy the rest of your day.
thanks for the opportunity.
Sure.
Thanks, Michael. Yep. Thanks, Rohit.